Okay, this is the last video for Chapter 8, and we've been talking about chemical reactions, looking at how to write chemical equations from chemical change descriptions, what things to look at in a chemical equation, like reactants go to products, special conditions, the coefficients of the balanced chemical equation, how to read those and what they mean. We balanced some chemical equations, and then we looked at types of chemical reactions. We looked at combination and decomposition, and then we looked in detail at predicting products or whether reactions would occur for single displacement and double displacement double displacement reactions. So now we're going to finish the chapter talking about the hidden or unseen element of a chemical reaction, which is heat. Because we can see starting materials or reactants, we can see products, we can see changes occur as far as seeing bubbles formed or color changes or precipitation. One thing that we can sense by either filling or monitoring with a thermometer is changes in heat in a chemical reaction by monitoring temperature changes. But we can't see heat. So that's what we're going to be looking at here. Most chemical reactions involve a change in the overall heat in the system. Either chemical reactions will absorb heat, okay? The reactants will gain heat from the surroundings, or the reaction will produce heat, which means it will release heat. It will get hot. So in almost all chemical reactions, there's going to be some change in heat overall. So what is it called? What is a reaction called when it absorbs heat? Well, thermal energy is related to heat energy. So we're going to use that base word thermic. So if something absorbs heat, it means that heat's going into the reaction. That reaction will be referred to as an endothermic reaction. Endothermic. Heat is entering or going into the reaction. Here's an example. If you react oxygen with nitrogen, oxygen plus nitrogen will form nitrogen monoxide. That reaction will not occur without input of heat. The reaction will absorb heat. So this is referred to as an endothermic reaction. The heat, when you have a endothermic reaction, and remember the heat unit's a joule, or typically the kilojoule on a large scale, is going to be a reactant. So when heat is a reactant, it's entering the chemical reaction. Heat's going into, it's an endothermic. See how I did that? It's into endothermic, entering. Now, when heat's released from a chemical equation or a chemical reaction, we say that it's exiting the chemical reaction. It's not going into, it's exiting. We're going to call this an exothermic reaction. Heat is exiting the reaction. It's a product. So in an exothermic, I don't know why I wrote that way. Let me write that again. I talk and write at the same time. It gets kind of bad. So exothermic. Don't talk and write at the same time. It's like don't text and drive. It's just as bad. Okay. Exothermic reactions release heat. Heat exits the system. So here, heat is going to be a product. It's the unseen product, but you can feel it. Heat's being produced in the chemical reaction. All right. When heat is produced in a chemical reaction, how much heat's produced? Remember, chemists are not only qualitative. They don't want to know only what's happening. We also always want to know how much. We want to know the quantity. It turns out when heat's produced or consumed in reaction, enters or leaves, that it does so stoichiometrically. Let's write that word down. Stoic. Here's stoic. I-O, metrically. Stoichiometry is a process of using a balanced chemical equation to give the quantitative amount of each reagent that enters and exits a reaction. Basically, it's the amount of something used or the amount of something produced according to a balanced chemical equation. it turns out that heat, being part of a chemical equation, is a part of a balanced chemical equation. What do I mean by that? When I say that heat is, produced stoichiometrically, in this reaction above it says 2 aluminums plus 1 iron 3 oxide yields 2 irons plus an aluminum oxide plus 852 kilojoules of heat. You see that right there? All right. So what stoichiometry is, it's the mole ratio between the reactants and products. And basically, let's say that I have 1 mole of iron 3 oxide going into my chemical reaction. According to this chemical equation, for every 1 mole of this reactant, we produce 852 kilojoules of heat. What happens if I double the reaction? What happens if I add 2 moles of everything, like 2 moles, or twice as much of all the reactants? I'm going to produce twice as much heat in the reaction. Well, what happens if I triple the amount of the reaction? So instead of 2 aluminums and 1 iron 3 chloride oxide, I have 6 aluminums and 3 iron 3 oxides. If I triple the reaction, I triple the amount of heat produced. That's what it means to be a stoichiometric. It's balanced according to the proportions of the balanced chemical equation. So heat is quantitative according to a balanced chemical equation. You can measure how much will come out. And you can predict, depending on how much of the reactants you add, how much heat you're going to get out or how much heat's going to be absorbed. So that's what we mean when we say heat is either produced or consumed stoichiometrically. It's part of the balanced chemical equation. Let's see here. The next thing is that the amount of heat that's absorbed or released in a reaction has a term. It's called the heat of reaction. Pretty easy to remember. Heat of reaction. The heat of reaction is the amount of heat that's overall absorbed or released. All right? Okay, so there's a symbol for heat of reaction. The overall change in heat, whether released or absorbed, is going to be called delta H RXN. RXN is a chemist's really fast way to write reaction. It's our favorite symbol to use. Because you use the word reaction so much in chemistry. We just say RXN. It means reaction, like prescription or anything like that in the medical field. Okay, so this is the symbol that stands for the overall heat of reaction, or the change in heat. Heat absorbed or heat released. Let's go back and look at these two reactions again. Here we said we had, and I accidentally erased it, an endothermic reaction in which heat enters the reaction. When heat enters the reaction, that means that heat is absorbed by the system. So we always say that heat's going to enter. We will have a positive heat of reaction value. So whatever that number is, if it's 181 kilojoules, we would say the overall heat of reaction is a positive value. Okay? Now, if the heat of reaction is given for an exothermic reaction, the heat is leaving the system. It's kind of like you have a bank account. Oh my gosh, all my money left the bank account. You would say that you would have a negative balance, right? So the same thing's true here for the heat of reaction. If you have heat leaving a system, it's always a negative value. You lose the heat to the surroundings. So here, whenever you have an exothermic reaction, heat's produced as a product. If I asked you what the heat of reaction would be, you would say negative 852 kilojoules. So realize that the heat of reaction, the heat absorbed, or the heat released, just like those energy values we studied with exam 1, energy can be positive or negative. Remember that heat's a form of energy, so it can be positive or negative as well. It has a sign associated. There's one more thing I want you to know, and it's called the activation energy of a reaction. Activation energy. And the symbol for activation energy is E for energy, sub A for activation. What in the world is this? And the activation energy is different than the heat of the reaction. The heat of the reaction is the overall absorption or release of heat when you combine all the different heats going on. And activation energy is the amount of energy needed to start a reaction. Now, why is this important? Almost every chemical reaction, whether or not energy is endothermic or exothermic, requires a certain amount of heat to get the atoms or the ions moving so that they'll rearrange. So basically, energy is needed to move atoms or ions so that a chemical reaction can take place. Bonds have to be broken before new bonds can be formed. In order to break a bond, that requires energy to be used. That energy needed to get the reaction started, the bonds broken before they can reform, is called activation energy. Now, the best way to learn the difference between activation energy and the heat of reaction, exothermic versus endothermic, is to look at something that chemists use called energy diagrams or reaction diagrams. Alright, so we have two reaction diagrams here. These two reaction diagrams look very similar to one another, but they're a little bit different, aren't they? They're mirror images of one another. What we're going to do is we're going to look at the one on the left first. The reaction diagram on the left is a reaction diagram for a generic exothermic reaction. So we're going to be looking at what happens when we have an exothermic reaction. Now remember what exothermic means. It means that overall heat is released. The overall heat of the reaction is going to be negative because you're going to be losing heat. Now let's look at the diagram. The first thing I do is if I ever look at a diagram or a chart, I always look at the axes first. So we have the y-axis here, and this one got cut off, so I'm going to write what it is. It's potential energy. Now remember what potential energy is in chemistry. It's the energy stored in chemical bonds. So if you have reactants or you have products, there's going to be chemical bonds holding some of those atoms together. The amount of energy stored in those chemical bonds will give you the overall potential energy of either the reactants or the products. Now on the x-axis here, we have time. This can be picoseconds, like electron transfer reactions. It could be, that's 10 to the negative 12th. It could be seconds, reactions between two different chemicals. Maybe a single replacement reaction. It could be hours, like an oxidation experiment in organics sometimes takes hours. It could be years. It could be millions of years, okay? So reactions take different amounts of time. So we're not going to put units on this because this is just a standard chart. But we're basically graphing the energy of the reagents versus time. As time goes by in a chemical reaction, you're going to go from your reactants to your products. So at the beginning of the reaction, you always start with your reactants. The bonds are all formed and everything's there. As the reaction starts to occur, well, notice they're at a certain potential energy. As the reaction starts to occur, though, the reactants bonds are going to break. And that's going to require energy. So see how the energy starts going up, the energy of the system? This is bonds breaking. All the reactant bonds need to break in a chemical reaction before they can be reformed. And that requires energy to break something. Like if you break a pencil in half, doesn't that require energy? Yeah. So the energy goes up. Once all of the bonds are broken, now bonds can start to be reformed for your product. So when the bonds start to get reformed, we start going downhill because bonds store energy and you get lower in energy. They become more stable again. Okay, so you become more stable, everything's becoming full octets and everything again, you know, all that good stuff. And at the end of the reaction, you form products. Okay, now, so we have our product energy, we have our reactant energy, according to the left-hand side of the diagram there. All right. So reactants are always on the left, products are always on the right, just like a chemical reaction. Now overall, if you take the energy of the reactants and you compare it to the energy of the products, when you go from reactant to product, if you go down in energy, see how we went down in energy? That means that heat is released. You went down in energy, you released energy or heat. delta H of your reaction is negative. You went down. This, going from a higher energy to a lower energy, releases heat. This is what tells you you have an exothermic reaction. You go down in overall energy. You release the energy. All right. Now, there's one other part of this curve I want you to know. When you take the energy of the reactants, so here, and you compare it to the highest energy point on the energy reaction curve, see how it goes up initially? This amount of energy is the activation energy, the energy needed to break all the reactant bonds to get the reaction started. So the highest point on the curve is actually, some of you might have taken some biology classes. They talk about this when they talk about delta G and how reactions occur. I know that I first encountered this in biology, that's why I say that. But this is really a chemistry thing and a physics thing. And it's a biology thing too, it's a science term. The highest point on any reaction curve is always, the highest energy is always called the transition state. Because everything's in transition. You don't have stable reactants, you don't have stable products. Everything's broken, everything's high in energy. You're in transition. So the highest energy state on this curve is called the transition state. Go from the energy of the reactants up to the transition state. That amount of energy change is called the activation energy. Okay, let's erase this and let's look at it again. So if you have a chemical reaction diagram, if you have a reaction diagram and you don't know if it's endothermic or exothermic, what you do first is you say, well, here's my reactants and here's their energy. Here's my products on the right, because we always go from reactants to products in time. And you say, okay, did I lose energy? Did I go up in energy from reactant to product, or did I go down? And we see here that we clearly went down in energy. The difference between the reactant and product energy is called the delta H of the reaction, the heat of the reaction. And because it went down, we lost energy. It was negative. It's an exothermic reaction. And then again, we said the amount of energy it takes to get the reaction started, to get to the transition state, is called the activation energy. So these are parts of the curve you should be able to recognize, you should be able to label. If I give you a curve like this, you should be able to recognize that it's an exothermic reaction too. Okay, now everything I just said applies to the next energy diagram as well, or reaction diagram. Once again, we've got time on the x-axis. On the y-axis, we have potential energy. All right, where are your reactants? Reactants are always on the left at the beginning of the reaction. And where are your products? The products and their energies of the products are always plotted on the right-hand side. Can you find the transition state, where you're in transition? All the bonds are broken, but none of them are being reformed. It's your highest energy point. That's your transition state. Okay, what's the activation energy? It's the amount of energy needed to activate or get the reaction started, to get over the hill, we would say. And so it's always from reactants to the highest point on the curve. This is your activation energy, the amount of energy to get started. Okay, where's your heat of reaction? Heat of reaction is always the reactant energy minus the product energy. Or products of energy minus the reactant energy, I should say. Sorry. So the heat of the reaction is always products minus reactants. Here, did we go down in energy or did we go up? The reactants to form products went up in energy. And when you go up in energy, that means energy was absorbed. The reaction system gained energy. So the heat of reaction is going to be positive. We absorbed energy into the system. It had to come from somewhere to get higher energy products. So when we absorb energy in the system, that's known as an endothermic reaction. Okay? So there's two types of energy curves. Basically, these are the two energy curves I could give you. An exothermic one or an endothermic one. We always say that exothermic reaction diagrams, by the way, go downhill. So we go from one energy to a higher energy to a lower energy. Exothermic reaction diagrams will eventually go downhill. Endothermic reactions, we always say, go uphill. It's an uphill reaction overall. That's literally how a chemist would, it's jargon that we would use. We would say, well, this is an uphill reaction, or it goes up in energy. it's endothermic. This goes downhill, it's down in energy, it's an exothermic reaction. Alright, so be able to understand how heat is involved in chemical reactions.